Hello viewers, in today's session we are going to discuss another important and very conceptual problem from definite integrals, right? And in this session we are going to discuss this problem where we are given a function f from closed interval 0 comma 5 to the set of real numbers, and this function f is given to be continuous, right? And moreover we are given that the value of the function f at x is equal to 1, that is f of 1 is equal to 3, and we are given another function phi of x, which is defined as phi of x is equal to integral 1 to x t cube g of t dt, where g of t is defined by this expression, that is g of t is equal to integral 1 to t f of u du. Then we have to find out the value of phi double prime of 1. So viewers, let us see how easily we can solve this problem by using a simple concept from definite integrals, right? See, we know from the theory of definite integrals that if we have a function, say capital f of x is given by the integral a to x f of t dt, then if we differentiate f of x with respect to x, then we get f prime of x is equal to f of x, right? So this is a famous theorem in definite integrals. If we are given a function capital f of x is equal to the integral a to x f of t dt, then the derivative of f of x, that is f prime of x, is equal to the function f of x, right? So here we are going to utilize this concept, and moreover here we can also use the concept of derivative. So now let us start with this function phi of x. So we are given phi of x is equal to integral 1 to x, and here we have t cube g of t and dt, right? So let us differentiate both sides with respect to x and using this concept. So now let us compare this integral with this one. So here we have x, here also we have x, and here we have 1, here we have a. So a can be taken as 1, and this function can be taken as f of t. So f of t is t cube g of t. So if we differentiate both sides with respect to x, then due to this result, we can get phi prime of x is equal to f of x, right? And here we have f of t, so this is f of x, and f of x can now be written by replacing this t by x. So we have here x cube, and then we have g of x. So we have obtained the derivative of phi of x. Now let us differentiate both sides again with respect to x. So now we have phi double prime of x, and here we have d by dx of x cube, and here we have g of x. Now in order to differentiate this function, we can see that this is the product of two functions, right? So using the product rule, so here this function x cube can be taken as u, and g of x can be taken as v. So we have first function, that is x cube, then the derivative of g of x, and then we have g of x and derivative of x cube, right? So phi double prime of x is now x cube, and the derivative of g of x can be written as g prime of x, and here we have g of x, and the derivative of x cube is 3x square, right? So now we have obtained the expression for the second derivative of phi of x. Now we have to find out the value of phi double prime of 1. So replacing this x by 1, we can now write phi double prime of 1 is equal to 1 cube, taking x is equal to 1 in this expression. And here we have g prime of 1, then we have g of 1, and here we have 3 times 1 square, right? So 1 cube is 1, and we are left with g prime of 1, and here this is also 1, so we have 3 times of g of 1, right? So to get the value of phi double prime of 1, we need to find out g prime of 1 and g of 1. So now consider this function g of t. So we have g of t is equal to 1 to t, and here we have f of u and du, right? And again, if we differentiate both sides with respect to t, then we can get g prime of t is equal to f of t, again using this result, right? Here we have f of x, here we have g of t, and then the integral a to x, here we have 1 to t f of u du. So differentiating both sides with respect to t, g prime of t is equal to f of t, right? Now see here, t is a dummy variable, so we can replace this t by x also. So we can now write g prime of x is equal to f of x, right? And here we have g prime of 1. So if we replace x by 1, then we have g prime of 1 is equal to f of 1, right? Taking x is equal to 1 in this expression. So g prime of 1 is equal to f of 1, and from here we can see that in the given problem we are given the value of f of 1 as 3. So here we can take 3. So g prime of 1 is equal to 3. So here we can replace g prime of 1 by 3, and then here we have 3 times g of 1, right? So now we need to find out the value of g of 1. So again, taking the help of this expression, we can find the value of g of 1. Now see, if we replace this t by 1, right? Or before replacing this t by 1, we can also write this function as g of x is equal to the integral 1 to x and f of u and du, right? So if we take x by 1, or replacing x by 1, we have g of 1 is equal to integral 1 to 1, taking x is equal to 1. Here we have f of u du. Now we can see that both the limits of integration are same or identical, so the value of this integral must be equal to 0, right? So g of 1 is equal to 0. So here for g of 1 we have 0. So now this is 3 plus 0, that is equal to 3, right? So the value of phi double prime of 1 is equal to 3. So viewers, this is how we can easily solve these kind of problems using this concept. Hello viewers, in today's session we are going to discuss another important and conceptual problem from integration. And in this session we are going to discuss this problem where we are given a function f of x which is defined by this equation: f of x is equal to cosine x minus pi square sine x integral 0 to pi by 2 f of t dt, then we have to find f of x, and further we have to show that this function f of x is strictly decreasing in this interval, that is 0 to pi by 2. So here first we'll find out the form of the function f of x, and then we'll see how we can prove that this function f of x is a strictly decreasing function in this given interval, right? So let us start with this equation. See, here we have f of x is equal to cos x minus pi square sin x, and here we are given this integral, right? So let us take this integral as say alpha. So we can take alpha is equal to 0 to pi by 2 f of t and dt, because whatever be the function f of t, when we calculate this integral is going to give us some number, say alpha, right? So taking this integral as alpha, we can now write this equation in terms of alpha as f of x is equal to cos x, then we have minus pi square sin x, and here we have alpha, right? Now let us observe this equation. Now this equation is f of x is equal to cos x minus pi square sin x alpha, right? So this is a function of x, and here if we replace this x by t by considering or by using the concept of dummy variables, and if we replace this x by t, then we can easily get f of t is equal to cos of t, then we have minus pi square sin t, and here we have alpha. So this is our equation number 2, right? Now let us substitute this value of f of t in this equation. So we can now write alpha is equal to 0 to pi by 2, and for f of t we can now write cosine t minus pi square. We can take alpha in front of sine t. So here we have alpha, and then we have sine t, and here we have dt. So now we have to evaluate this integral. Now the integral of cosine t is simply sine t, and here pi square alpha is a constant, so we can now write pi square alpha, and the integral of sine t is minus cos of t, and the limits of integration are from 0 to pi by 2. So in other words, we can also write this equation as 0 to pi by 2 cos of t dt, and then we have pi square alpha and 0 to pi by 2 sin t dt. So we can also write this integral like this, or integrating the terms, cosine t has integral sin t, and sin t has integral minus cosine t. So now we have sin t, and here minus and minus multiplied together gives us positive sign, and here we have pi square alpha cos of t, and limits of integration are from 0 to pi by 2. Now let us substitute the limits and taking the difference. So the value of alpha is now sine pi by 2, then we have pi square alpha cos of pi by 2, and then we have minus sine of 0 plus pi square alpha, and here we have cos of 0. Now sine pi by 2 is 1 and cos pi by 2 is 0, so this term is 0, and then sine 0 is 0, and here we have cos 0 is equal to 1, so we have simply pi square alpha times 1, that is pi square alpha. So now we have alpha is equal to 1 plus 0 is 1, and here we have minus pi square alpha, and solving this equation for alpha, we can now write alpha plus pi square alpha is equal to 1, alpha, taking alpha common, we have 1 plus pi square is equal to 1. So alpha is equal to 1 over 1 plus pi square. So now getting the value of alpha is equal to 1 plus pi square, we can easily conclude that the value of this integral, that is 0 to pi by 2 f of t dt is equal to 1 over 1 plus pi square. So this is also an important deduction from the value of alpha. Now let us substitute this value of alpha over here. So we have f of x is equal to cos x minus pi square sin x, and here we have alpha is equal to 1 over 1 plus pi square, right? So this is the required form of the function f of x. So f of x is defined as cosine x minus pi square sine x over 1 plus pi square. So now to prove the second part, that is f of x is a strictly decreasing function in 0 to pi by 2, we have to differentiate this function f of x. So the derivative f prime of x is equal to the derivative of cosine x is minus sine x, and the derivative of sine x is cosine x. So we have pi square 1 plus pi square, and sine x has derivative cosine x. Now taking negative sign outside these two terms, so we have sine x plus pi square over 1 plus pi square and cosine x, right? So from this expression we can see that f prime of x is going to be less than 0 for all values of x belonging to this interval, that is 0 to pi by 2, because this interval it gives us the first quadrant, and in the first quadrant that is sine x and cosine x both are positive. So in the first quadrant we have sine x and cosine x both being positive. So this term is going to be always positive in this interval, and here we have the negative sign. So f prime of x is always less than 0 for all values of x belonging to this interval, and this is the condition for a function to be a strictly decreasing function. So if the slope of the tangent is negative, then the function is said to be a decreasing function. So this is how we can prove that the function f of x is a strictly decreasing function in this interval, because the derivative is negative or it is less than 0. Hello viewers, in today's session we are going to discuss another important and conceptual problem from integration, and in this class we are going to discuss this important problem where we are given a function f which is defined as f of x is equal to 1 plus 1 over x times the integral from 2 to x, and we have f of u du, and we have to find out the value of f of e, right? So here what we will do, we'll first solve this equation, and to get the form of the function f of x. So once we get the function f of x, we can easily find out the value of f of e by substituting x is equal to e, right? So to solve this problem, we have to make use of the concept of derivative and an important theorem from definite integrals, right? So let us solve this easy problem by using the concept of derivatives and definite integrals. So let us first multiply throughout by x, right? So we have the equation f of x is equal to 1 plus 1 over x integral 2 to x f of u du. So let us multiply throughout by x. So we'll get here x times f of x, and here we'll get x, and then here we have this x and this x get cancelled, so we have the integral 2 to x f of u and du. So this is the first step in solving this equation. Now let us differentiate both sides with respect to x. So we have here d by dx of x f of x, and here we have d by dx of x, and here we have d by dx of the integral 2 to x and f of u du. Now here we can make use of the product rule, that is the derivative of the product of u and v, which are functions of x. We have u dv by dx, then we have v du by dx. So here the first function may be taken as u, that is x, and second is v, that is f of x. So we have x, the derivative of f of x is f prime of x, then we have f of x, and the derivative of x is 1, and here the derivative of x is 1, and here the derivative of this integral is simply f of x, because here we can make use of an important property from definite integrals, that is, if we have y is equal to the integral a to x, say f of u du, then the derivative of y with respect to x is given by simply f of x, right? So this property is being used over here. So we have here simply f of x. So now we have x f prime of x plus f of x, and this is equal to 1 plus f of x. Now f of x and f of x get cancelled, so we have simply x f prime of x is equal to 1, and f prime of x is equal to 1 over x. So now we have a simple differential equation here, that is d by dx of f is equal to 1 over x. So we can simply integrate both sides with respect to x. So we have integral df over dx, and here we can write dx, and here we have 1 over x dx plus c. C is the constant of integration, right? And f is f of x. So here we have simply f of x, that is f, and here the integral 1 over x dx is simply natural log of x, and c is the constant of integration. So now the function f of x is given by this expression, and we have to find out the constant of integration by using some condition, right? So here to get the condition, we'll here substitute x is equal to 2, right? So taking x is equal to 2 in the given equation, we can see that we have f of 2. Here we have x is equal to 2, then here we have 1, and here we have 2, here we have 1 over 2, and then 2 to 2 because x is 2, and here we have f of u and du. Now the value of this integral is 0, being because here the limits of integration are same. So the lower limit and the upper limit both are same, so the value of this integral is 0. So we have simply f of 2 is equal to 1. Half times 0 is 0, so this is simply 1, right? So when x is equal to 2, f of 2 is equal to 1. So let us impose this condition on this equation. So here, taking x is equal to 2, we have f of 2 is equal to natural log of 2 plus c, and f of 2 is 1. So here we have 1 natural log of 2 plus c. So c is equal to 1 minus natural log of 2. So taking this value of c in this equation, we can now write f of x is equal to natural log of x plus 1 minus natural log of 2. So our function f of x is now given by this expression, and we have to find the value of f of e. So let us take x is equal to e in this function. We have f of e is equal to natural log of e plus 1 minus natural log of 2, and natural log of e is 1. So we have 1 plus 1 minus natural log of 2, that is 2 minus natural log of 2, right? So the required value of f of e is given by 2 minus natural log of 2, and this value can also be expressed like this. We can write 2 as 2 times natural log of e minus natural log of 2, and this is natural log of e square using the properties of log, and here we have natural log of 2. So again, using the properties of log, we have natural log of e square over 2, right? So f of e can also be given by this expression. Hello viewers, in today's session we are going to discuss another important and very conceptual problem from definite integrals. And in this session we'll solve this problem where we are given a function f which is given to be differentiable function, and this function f of x, it satisfies this relation, that is f of x is equal to square root of 3 over 2 plus integral 0 to x square root of 1 minus f square u du, right? So here we have the function that is the square of the function f of u, and then we have to find f of pi, right? So let us see how easily we can solve this problem by using the concept of uh, derivatives and one important property of definite integrals. So let us start. So here we are given this relation, right? Now what we will do, we'll differentiate both sides with respect to x. So we'll write d by dx of f of x, and here the derivative of root 3 over 2 is 0 because it is a constant, and then we have d by dx of 0 to x and square root of 1 minus f square u and du, right? So dy dx of f of x is simply f prime of x, and here d by dx of this integral is simply equal to square root of 1 minus f square x. That is, we'll replace this u by x. So here we have used an important result from definite integrals, which says that if we have a function, say y is equal to the integral from a to x, and here we have say g of u du, then the derivative of y with respect to x is simply g of x, right? So if we compare this integral with this one, then the lower limit is a is equal to 0. Here a is a constant, and x, here the upper limit is x, here also the upper limit is x, and g of u is given by square root of 1 minus f square u, right? So when we find out the derivative of this integral with respect to x, then we simply replace this u by x. So we have now f prime of x is equal to square root of 1 minus square of the function, that is f of x. And now this is a differential equation of first order and first degree. So now we have to solve this differential equation to get the value of f of x. So now to solve this differential equation, let us write f of x as simply f, just for convenience, right? And f prime of x as df over dx. So we'll use these notations just for convenience. So f prime of x can be written as simply a df over dx, and here we have square root of 1 minus f square, right? So separating the variables, because this differential equation is variable separable form, right? So we can separate the variables. So we have df over square root of 1 minus f square, and here we have dx. Now integrating both sides with respect to, here we have x, and c is the constant of integration. Right now this is a well-known integral, because we know that integral dx over square root of 1 minus x square is equal to sine inverse x. So now the integral of df over square root of 1 minus f square is simply a sine inverse of f, right? And in the right hand side we have simply x, integral of dx is x, and c is the constant of integration, right? So now we can write f is equal to sine of x plus c, right? So now again using the usual notation for f as f of x, we can now write f of x is equal to a sine of x plus c. So this is the form of the function f of x, and we can see that f of x is a sine function. Now our next aim is to get the value of this constant of integration c, right? So let us find out this c with the help of some condition. So now let us take x is equal to 0 in the given equation, right? So when we take x is equal to 0 in this equation, we have f of 0 is equal to square root of 3 over 2 integral 0 to 0, and here we have square root of 1 minus f square u and du. Now clearly this term is 0, because here both the limits of integration are 0. So we are simply left with f of 0 is equal to square root of 3 over 2. Now let us use this condition to get the value of c, right? So what we will do, we'll take x is equal to 0, and f of 0 is equal to square root of 3 over 2 in this equation. So we have sine inverse, f is given by square root of 3 over 2, and x is 0, and here we have c. So we have c is equal to sine inverse square root of 3 over 2, which is equal to pi over 3, right? So sine 60 degrees, that is sine pi by 3, is equal to square root of 3 over 2. So the value of constant of integration c is equal to pi by 3. So let us take this value in this relation. We have f of x is equal to sine of x plus pi by 3, right? So this is our required function f of x, and let us find out the value of f of pi by taking x is equal to pi, right? So we have f of pi is equal to sine pi plus pi by 3, right? And sine pi plus pi by 3 is minus sine pi by 3, because we know that sine pi plus theta is equal to a minus sine theta. Now sine pi by 3 is root 3 over 2, and here we have the negative sign, right? So the value of f of pi is given by a minus square root of 3 over 2. Now here it is important to note that while calculating the value of the constant of integration c, we have taken x is equal to 0, and f of 0 is equal to square root of 3 over 2, right? And if we take x is equal to 0 in this equation, then we have f of 0 is equal to sine 0 plus c, that is simply equal to sine c, and f of 0 is root 3 over 2. So here we have root 3 over 2 is equal to sine c, right? And root 3 over 2 is equal to sine pi by 3, and we have now this equation, that is the trigonometric equation, sine c is equal to sine pi by 3, right? So if we use the concept of general solution of this differential equation, this trigonometric equation, then we can write c is equal to n pi plus minus 1 raised to n, and here we have pi over 3, right? So if we take the general solution and we have to find out some other values of c, then we can also make use of the concept of general solution of this trigonometric equation. So in that case, c is given by n pi plus minus 1 raised to n pi by 3. So in the present case, we have just considered the value of c corresponding to n is equal to 0. So when we take n is equal to 0 in this general solution, then the value of c is simply given by pi by 3, right? And in that case, the form of the function f of x is given by sine x plus pi by 3. So to summarize this discussion, we can easily conclude that as per the requirement of the given problem, we can use the different values of C from this general solution, right? So assigning different values to n, we can obtain different values of this constant of integration c, and accordingly the form of the function f of x can be taken. So in the present case, we have just taken n is equal to 0, and corresponding to n is equal to 0, we have c is equal to pi by 3, and our function is given by f of x is equal to sine x plus pi by 3. So accordingly, using this relation, we have calculated the value of f of pi.